Please welcome Chad Davis, who will talk about the distribution of tau congruent numbers.
Thank you. So, this is on the distributions of tau congruent numbers. This talk is dedicated to Dr. Blair K. Spearman, who unfortunately passed away on October 1st of last year. These were some problems that we were working on together. So this one is for the memory of Blair. Okay? Okay, so what are we doing today? We'll start off introducing congruent numbers. I'm sure everybody here knows what a congruent number is, but we'll start easy. Why not? So we'll look at those, and we'll look at what the tau congruent numbers are. And then we'll be able to look at distributions of tau congruent numbers and tau congruent numbers whose associated elliptic curves are ranked at least 2. Okay? Okay, so congruent numbers start by introducing the congruent number problem. The problem asks, which positive integers n can you realize is the area of a right triangle with rational side lengths, rational sides? Such integers n are called congruent numbers. And John Coates has described this as the oldest unsolved major problem in number theory, and that quote goes on to say, and perhaps all of mathematics. So this is a nice problem, interesting problem, lots of people have done work on it. So how do you check if something is a congruent number? Well, we have the following theorem. It connects congruent numbers to elliptic curves. In particular, we have that if n is a positive integer, then n is a congruent number, if and only if this elliptic curve here, En, well, this is going to take some time, there we go, En, given by y squared equals x times x squared minus n squared, contains a rational point of order different than 2. En here is called the congruent number curve or the congruent number elliptic curve, whichever you prefer. So this is nice. It connects this problem about areas of triangles to a problem about elliptic curves, right? And I think a lot of the analysis on congruent numbers now is done via analysis of these congruent number curves. Okay? In particular, I know these two results were, and these two results are the ones I want to focus on for today. The first was proved by Bennett. It says that if m bigger than 1 is an integer, then there are infinitely many congruent numbers, distinct modulo squares of rational numbers, contained in every residue class modulo m. And the second one was proved by Blair and Jennifer Johnstone. And it says the same thing as Bennett's theorem, except it adds a stipulation that the corresponding congruent number curves have to have rank at least 2. Okay? So the goal for today is to give generalizations, or, well, I'm going to give a generalization and an analog of these two theorems to the tau congruent number. So you ask, okay, well, what is a tau congruent number? So I'll introduce these via the so-called tau congruent number problem. This problem arises by replacing the assumption of right triangle with rational sides in the congruent number problem with any triangle with rational sides. Okay? So more precisely is stated as follows. Which positive integers n can be realized as the area of a triangle with rational sides? Okay? And these guys are called tau congruent numbers. Now, this is slightly mysterious. Why would these things be called tau congruent numbers? Where does tau come from? Tau comes from this theorem here, which was proved by Goins and Matthews. It says as follows: a positive integer n is the area of a triangle with rational sides, if and only if there is a non-zero rational number tau, such that this elliptic curve, En tau, has a rational point of order different than 2. En tau here is called the tau congruent number elliptic curve, or just the tau congruent number curve. And this is really nice, right? It's very similar to the characterization we had for congruent numbers and elliptic curves. Very simple, very nice. So from this guy, you can get two nice lemmas, which are really more of just observations, but I'll call them lemmas. I won't be too cheap about it. The first one says that a positive integer n is a congruent number, if and only if it is a tau congruent number for tau equal to 1. And this is obvious from this guy here. If we sub tau is equal to 1 into the tau congruent number curve, you get exactly the congruent number curve. So that fellow's obvious. Nonetheless, it's a nice observation because it tells us that these tau congruent numbers are really a very appropriate generalization of the congruent numbers, right? Because the congruent numbers follow as a special case. The second lemma is also kind of obvious from the geometry of the situation. So it says if we fix tau and q star, non-zero rational, and we let n and e be positive integers, then n is tau congruent if and only if n times e squared is tau congruent. And as I say here, it's easily verified that if you have some rational point, x naught, y naught, on en tau, with y naught non-zero, in other words, has order different than 2, this happens if and only if this fellow here, x naught e squared, y naught e cubed, is on the tau congruent number curve for n squared, and of course, y times e cubed, y naught times e cubed would not be 0, so it would have order. So the whole take-home point of lemma 2 is that you can take a congruent number, scale it by a square, you get a new tau congruent number. We're going to need that later, okay? Okay, so with these things under our belts, we can start talking about tau congruent numbers. The first result is proved by Blair and I. Towards this goes as follows. So that tau equal to c over d be a fixed non-zero rational number, c and d relatively prime. Then, for relatively prime integers Rs, we define this new integer here, nRs, cdrs times cr plus ds times dr minus c. Okay? Then, this fellow nRs is a tau congruent number with the most finitely many possible exceptions for r and s and z. Okay. Well, let's go through a quick sketch to see how we did this. So we start by looking at solutions to this binary quadratic form here. X squared plus n times tau inverse minus tau xy minus n squared y squared is equal to z squared. Okay? Now, using identities of Desbow, in fact, this fellow gave a complete solution to this binary quadratic form. We were able to find the following solution in integers given by these three guys here. Okay? Now, the nice thing about this solution is that x is a square, y is a square, which is great because taking square roots, you get a solution to this quartic equation here. Same thing, x is replaced with x squared, y is replaced with y squared. Solution given by x equal to root x, y is equal to root y, z is equal to z. Okay? Why is this nice? This is nice because this integral solution to this quartic equation exactly gives you a rational point on the tau congruent number curve for nRs. The point's coordinates are given by this one. X squared over y squared, xz over y cubed. And now we're very happy because we have a rational point on this elliptic curve. All we need to do to show that nRs is in fact a tau congruent number is show that this point doesn't have order 2, or has order 2 with the most finite many exceptions. So all you do is you take a pen and paper, or maple, or whatever, put in x, put in z, multiply them together, see when it's going to be equal to 0. And it turns out, with the most finitely many possible exceptions, the thing is never equal to 0. Okay? Conclusion, this fellow here, ENRS tau, contains a point of order different from 2 for all the finitely many possible exceptions. Therefore, n is a tau congruent number. This led us to the following. This is a generalization of Bennett's theorem. So again, this was proved by Blair himself. So that tau equal to c over d, fixed non-zero rational number, c and d relative to prime, same setup as before. And we let m bigger than 1 be an integer. Then there exist infinitely many tau congruent numbers, distinct modulo squares of rational numbers, contained in every residue class modulo. Okay, so, and we'll go through a sketch of this, it's not too bad. So we fix sum a between 0 and n minus 1. And we define this set, lambda a, to be the set of all lambda in the naturals, such that lambda is congruent to minus a modulo. Now, in the formula we had for nRs from the last theorem, we take r to be minus 1, and s to be cd m all squared times lambda. Then the theorem implies that n of lambda, which is just this fellow here, will be a tau congruent number for most finite and many possible exceptions for lambda. Okay? And this is great here, right? Because that fellow's a square. So get rid of the square, you get a new tau congruent number we'll call n tilde of lambda, given down here. With the most finite and many possible exceptions, reduce modulo m, and you exactly see n tilde is congruent to a mod. A was fixed as any congruent class modulo m. Therefore, this almost completes the proof of the theorem. The only thing that we still need to show from here, of course, is that infinitely many of these n tildes are distinct modulo squares of rational numbers. Without getting into too many of the details, we'll summarize as follows that if that were not true, then you would wind up finding a finite family of elliptic curves, and on at least one of those curves, you would have infinitely many integral points, which is, of course, contradicting Siegel's theorem, right? Therefore, we must have infinitely many of these guys. The n tildes are the same modulo squares of rational numbers. Completes the proof of the theorem. Okay, so just a note about this. If in our formula for n tilde here, we take c and d equal to 1, in other words, tau is 1, then n tilde becomes a congruent number. But moreover, is not just any congruent number, is exactly the congruent number that Bennett used to prove his theorem. Which is kind of nice. So we were very happy about this because it told us, oh, that's great. That means we kind of have the correct generalization of Bennett's theorem, right? His congruent numbers are kind of a special case of our tau congruent numbers. So we were very happy about that. Okay, so we were happy, but I wasn't that happy, I guess, because I had to push it and say, well, can I build the rank up of these elliptic curves to have rank at least 2, right? Can I do this? Well, yes. The first result regarding this is as follows. So I proved this. So we let tau, same setup as before, equal to a over b be a fixed non-zero rational number, a and b is relatively prime. Pick p and k and z, fix them, they're non-zero integers, and let L and z be any integer. You define this kind of unpleasant looking fellow here, g of lambda, be this guy, and we'll take lambda of L to be k times pl plus 1 over the 4th power, and define n of L to be the integer minus lambda of L times g evaluated at lambda of L. Okay? We consider the following elliptic curves over Q, ENL tau, which is just tau congruent number curve for n of L. Then ENL tau has rank at least 2 for all the finitely many values of L and Z. Okay, so how did I go about doing this? So I guess there's lots of ways you can show curves have, or calculate ranks of curves, but I just went with a 2 descent. So I will go, okay, so I'm going to do a 2 descent to calculate the ranks here. And if I tell you that, then you probably look at me and go, well, you better have some rational points on your curve if you want to do this, right? And I go, yes, I do have rational points on the curve. I have T1, which is 0, 0, and T2, which is NL tau 0. These are 2 kind of trivial rational points on the curve. We also have P1 and P2, which are non-trivial rational points on the curve. And their x-coordinates are given by these 2 sort of monstrous looking things down here. So I have 4 points on the curve. And what is the point from here? Well, if we let alpha denote our fundamental 2 descent now from the group of rational points on ENL tau to Q naught Q star squared, then the idea is to show that the multiplicative group generated by the images of T1 and T2, P1 and P2, here alpha, contains 16 distinct elements. If you can do this, that means that the image of the group of rational points on ENL tau has at least 16 distinct elements in it, and which exactly implies that the rank of ENL tau is at least 2. Okay? Now, how on earth did you do this? It basically came down to just repeated applications of Siegel's theorem over and over and over again. And I'll give an example to show how I did this. So the idea was basically this. Let's suppose that I want to take alpha of P1 and show that that's not congruent to the identity element in Q1 Q star squared. Okay? So what do? You take alpha, apply it to P1. What do? You get the square free part of the x-coordinate of P1, modulo Q star squared. So I get this fellow here, mod Q star squared. And if I want to show that that's not congruent to 1 mod Q star squared, I need to show that this fellow, come on pointer, don't fail me, right there, is not a rational square, right? So take that guy, set it equal to a square, expand it out, and you see you get, it was either a genus 2 or a genus 3 curve, I can't remember. But it was a higher than 1 genus curve in the variable L, okay? Now, if L is in Z, and I plug L into this guy, and I get a square out, well, all the coefficients are integers, means that I have to get an integer square back in. Therefore, a solution to this guy being equal to a square, if L is an integer, means that I'm getting some entry point on genus 2 curve. There's only finitely many of those by Siegel's theorem. Therefore, there can only be finitely many L and Z such that this guy is congruent to 1 mod Q star squared. In other words, alpha P1 is not congruent to 1 mod Q star squared, and it is for finitely many values of P possible. And that was basically the whole idea behind doing this. So all you do is you kind of repeat the same argument, just showing that all of these guys' images are all distinct, okay, and distinct from one another. You don't need to do it for all 16 possible combinations, of course. You just show the general congruent to one another, and that's good. Okay, so from here, and I'll call this a corollary because it's not quite a full generalization, I got the following corollary, okay? So we let tau, again, same setup, fixed non-zero rational number A and B relative to prime. Let P and Z be fixed with P bigger than 1, then there are infinitely many tau congruent numbers contained in every residue class modulo P, whose corresponding tau congruent number curves have rank at least 2. And the proof is actually quite quick. It goes exactly as follows. If we fix K and Z, and we take NL to be that fellow right there, then by the previous theorem, NL is a tau congruent number and its corresponding curve has rank at least 2. Furthermore, you reduce modulo P, you see exactly NL is congruent to K mod P. K was fixed in Z arbitrarily, so this suffices as proof for infinitely many and any residue class modulo P. Okay. Now, like I say, I call this an analog because I kind of didn't do one step in this that was in Spearman and Johnston's theorem, right? I haven't shown that infinitely many of these tau congruent numbers are inequivalent modulo squares. You might ask, why didn't I do that? And the honest answer is because I forgot. It was kind of an oversight on my part when I was doing this problem. I got so happy that this even worked that I didn't really think of it. Oh well. But the point is, for this guy, now I haven't sat down and worked it out explicitly, but I'm almost 98% confident that the exact same argument in the previous theorem will carry over here. So we should be able to append infinitely many distinct modulo squares without causing ourselves too much pain. Though I can't say that with 100% certainty at the moment, but it should be okay. All right, so this is great because we've now done exactly what we wanted to use. Right? Generalized Bennett's theorem gave an analog of Spearman and Johnstone's theorem. So what are some possible future directions we can go in from here? There's a number, of course, right? The natural one is to say, well, if you can build up to rank 2, can you go to rank 3? You go to rank 4, et cetera, right? You could also ask about theta congruent numbers, which are more of an even bigger generalization for tau congruent numbers. So for the theta congruent numbers, Bennett's theorem's already been generalized to them. But could you do the second theorem? Right? There's another possible direction. If we want to get away from these distributions, another question that I have asked and haven't yet found any solution to is, could you find an arithmetic progression, non-trivial arithmetic progression on the tau congruent number curve? This has been done for congruent number curves. So it'd be interesting to see if you could do this for the tau congruent number curves. And in fact, the solution to that might actually give you a solution for the rank 3 question. Okay, that's it. Thank you very much. I will say one thing though. I have a little bit of time. About this tau here, because it still is a little mysterious where that number comes from. Tau depends on what of the angles of the triangle you're looking at. So attached to any triangle, you could possibly get 3 different tau congruent number curves. And the interesting thing about those is that you might get 3 different curves, or you have 3 different curves attached, and those curves can be actually vastly different. In the paper by Goins and Mattis, they give an example where the same triangle has 2 tau congruent numbers.